Next topic is the basic angular momentum consideration. Work can be written as the force times the distance is the work, or torque times the angular velocity. I think that is the if if the shaft torque and rotation of the rotor are in the same direction, energy is transferred from shaft to the rotor and from rotor to the fluid. In this case, the machine is a pump. Okay. Conversely, if the torque exerted by the shaft on the rotor is opposite to the direction of the rotation, energy transfer from the fluid to the rotor, in this case we call the turbine. Okay. From Breno transport theorem, the change of momentum inside control volume plus the change of momentum on the surface equal to the cross F. This term is no change inside the control volume. So we have just the second term. Explain that the right hand side is the net rate of flow of momentum, angular momentum through the control surface. Okay. In one dimension of flow through the turbo machine, rotor will with the section 1 at inlet and the section 2 at outlet result in this equation. The torque is equal to the mass flow rate times radius times tangent velocity between point 1 and point 2. So where this equation come from, we can derive from this one. You can see that from the transport theorem, we can derive that what is the equation of shaft, T shaft, and T1 is inlet and 2 is outlet. Okay, for this case, we can say that the T shaft is negative because of R1 is greater than R2. And if the mass flow rate is equal, V theta 1 greater than V theta 2. So in this case, it's a turbine. We got a negative pressure. And in case of pump, we expect the T sharp is the positive for pump. Because normally the inflow is the inside, from inside to the outside. Okay, that is the inflow at this point, and outflow at this point so it's positive because of the R2 is greater than R1. And because of increase of energy, V theta 2 is greater than V theta 1 because the brake push the fluid to increase the velocity. Okay, and the shaft torque is a direct proportion to the mass flow rate m dot. Okay, the more torque and power to pump water than to pump the air with the same volume flow rate. Okay, and that is one if because of the density of the water is greater than density of air and mass flow rate of water is more than air. So why the T sharp of water is greater than T sharp of air. And this equation for the work, the sharp power, okay, this equal to W dot sharp, the torque times the angular velocity. And we combine equation 2 and 3 to get this equation. T sharp and the W sharp is positive when T sharp and angular velocity are in the same direction and negative otherwise. Okay. And in case of work per unit mass, so we divided by mass. So we got this equation for the small W sharp. this shows the velocity vector at between v and v theta and vx. Okay, the angle, this is a 90-degree angle. Okay, and we from this we can look at the small right angles, and we can write the equation of the vx square equal to v theta subtract u square equal to w square, and we combine both equation together and combine with the equation 5, so we can write equation of the work per unit mass of this turbo machines. It depends on the velocity vector, we can on the absolute velocity, rate velocity and relative velocity. Next I will show you some clip about this, the self-propeller lawn sprinkler. Okay, can we apply the knowledge of the moment of momentum to explain the movement of this self-propeller lawn sprinkler? Okay.